Procedural analysis is an advanced optimization technique. It's typically used while a function call is being made to analyze whether what global data is being accessed by the function, what needs to be stored on the stack, which register needs to be preserved on the stack according to the ARM AAPCS convention, and which can be actually avoided from being stored. So that is one part of it. The second part is basically whether the call itself can be avoided and so on. So here is an example here where there is an array of 100 elements, and there are two variables C and D which are initialized to 100 and 10 respectively, and a function called bar is called, which iterates over 100 times and assigns the result of the function call foo to each of the array variables from 0 to 99. Now the foo itself does very little. It's just returning returning a by b, integer division of a by b, and the result is stored in array function. If you look at the optimization with the procedural analysis, basically it can store the temp. So this function call is doing nothing but a by b in every time it is called. It can be stored in a temporary variable, a temp equal to c by d, and it can be used for assigning. Then there is also loop unrolling. Basically, it trades off the number of instructions with a branch overhead. So the original loop is 100 times. Here it is actually divided into 25 iterations with 4 different elements being assigned in each iteration. So this is typical loop unrolling. And so there are two effects here. The procedure analysis suggests that this function is not doing, and it's actually having an invariant value, which can be, so the whole function can be replaced by a temporary variable, which can be assigned to all the elements, and the assignment itself is done by unrolling the loop to 1/4. Basically 4 statements, and the number of loops is 1/4. Here is the example code, which is basically the main function initializing two variables, local variables C and D to 110 before calling the function bar. The function bar is iterating 100 times over all the elements of the array, assigning each element with the return value from the call to the function foo. Function is called with parameters C and D. If you look at foo, basically it is doing a ratio of the first parameter to the second parameter. Now here is the disassembled code. So it starts with initializing C to 100 and D to 10. After that, there is the index variable, which is stored in register R2. You can see that it's the limit of the limit of the iteration is now 25 instead of 100. That means it's 1/4 of the loop termination value. Correspondingly, 4 different elements are assigned. You can see 4 store operations with offsets 0, 4, 8, and 12. So 4, each is a 32-bit address. So you can see that 4 array elements are being assigned values. The interesting thing is, if you see here, there is no function call to the function foo. The ratio C by D was computed, and that value is stored in R0, which is stored in each of the array elements directly. So there are two things that have happened. One is that the computation of C by D has actually three things have happened. The ratio of C by D is computed directly. You don't even see a division operation. That's because C and D values are known at compile time. These are basically, this is called constant folding. So the ratio C by D is computed at compile time. So there are no instructions generated for division. That is one optimization. That's called constant folding. The second operation is basically in terms of loop being, second optimization is in terms of the function call to foo has been replaced by the ratio C by D, which is stored in register R0, which is basically like a temporary variable. And then the third optimization is loop unrolling, where the loop iterations are being reduced to 1/4, and in each iteration, 4 elements are being assigned. So this is a very typical transformation that the compiler can do. A loop unrolling is always dependent on the trade-offs between execution time saved due to avoiding branching in the loop versus the number of repeated instructions that you have to include. So if here the compiler setting has been set for a balance, so balance between code size and execution speed. So it has made a decision to fold it 1/4.